In this video, we will take a look at the impact that thermodynamics has on the formation of solutions. So just kind of a brief review of thermodynamics. Remember that energy governs everything. So whether or not a process can occur naturally or on its own, whether it is a reaction, a phase change, solution formation, any of these things, it's all dependent on the overall change in energy, what we call Gibbs free energy. You might recall this from your first semester chemistry class. Gibbs free energy we represent with a delta G. This is the overall energy change, and it's impacted by temperature, enthalpy, and entropy. Now recall that enthalpy we represent with a delta H. It's the heat of our reaction. It's the heat that's getting transferred. If delta H is positive, that indicates that we've got a process that is endothermic and we are absorbing heat. If delta H is negative, our process is exothermic and we are releasing heat. Now, entropy is delta S, or the change in entropy is delta S. This is the amount of randomness or disorder in our system. If delta S is positive, particles are becoming more random. If delta S is negative, particles are becoming less random or more ordered. So both of these thermodynamic properties, enthalpy and entropy, they're going to impact what we call the Gibbs free energy, again, that overall energy change. Now, Gibbs free energy is defined as being equal to delta H minus T delta S. So we can see from that equation that both the enthalpy, the entropy, and the temperature are going to influence that delta G. If delta G is positive, then our process is non-spontaneous due to an overall energy gain, which is less stable. So non-spontaneous means it's not going to occur on its own naturally. Doesn't mean impossible, it just means it's not going to happen naturally. Now, if delta G is negative, our process is spontaneous due to an overall lowering of energy, which is more stable. So how does this impact solutions? If we're going to talk about the formation of a solution, the free energy associated with that solution formation equals the heat transfer as a result of that solution formation minus the temperature times the entropy of that solution formation. Now, the entropy is always going to be positive. Solids and liquids become more random as they dissolve. So we can see some examples of that in our image here. So if we started off with a solid, my particles are very compact. We dissolve it in our liquid. The particles are now separated. So as they're separated, they're going to be more random. With a liquid, we're mixing two liquids. We've got different particles. We go from having particles that are spread out, but now we've got different types of particles. They're going to intersperse amongst one another. It's going to be more random. So delta H for solution formation is always positive. Now, delta H could be positive or negative. That's going to come down to our intermolecular forces. It depends on solvent, solute, and solute-solvent interactions. So we talked about these with our intermolecular forces. So the solvent-solvent interactions are what holds our solvent in its physical state. Solute is what holds the solute in its physical state. The solute-solvent interactions will be what allows the two materials to mix. So to break the solvent-solvent interactions, it requires energy. To break the solute-solute interactions, it requires energy. It always requires energy to break attractions. But we've broken those attractions. Our particles, our solute and solvent are attracted to one another. When those attractions form, we actually release energy. So solute-solvent interactions release energy when they form. So it becomes a balance. Remember, we want, ideally, for our delta H to be negative. We want to be releasing energy. So if the energy released when the solute-solvent interactions form is greater than the energy required to break the interactions, then overall delta H will be negative. And if that's the case, that solution formation will be spontaneous. Now, if the energy released when the solute-solvent interaction forms is less than the energy it takes to break the overall interactions, then it's going to be positive. So it's going to come down to the strength of our intermolecular forces, and it's going to be impacted by temperature. We'll talk about this in a later chapter, but when it comes to that temperature, remember that's giving us more energy to break those attractions. So if we take a look at some problems, when dissolving lithium chloride in water, we notice a drop in temperature being observed. And based on this, we're asked, what is the sign of delta H? Why does our solution still form? So we need to review a couple of things. Remember when we talk about thermodynamics, we have our system. The system is always what we're interested in. And then we have our surroundings. So in the case of dissolving lithium chloride, the system is going to be the actual breaking of those intermolecular forces. Now this is occurring in a solution. The solution is going to be the surroundings. Now when we go to measure our temperature, we're not measuring at that individual bond level. We are measuring the surroundings. So this will generally be the case. We generally measure our surroundings and we relate it back to the system. Now, whatever happens to my surroundings, the opposite is occurring to my system. So if my system is transferring heat to my surroundings, the system releases that heat, but the surroundings are absorbing that heat. Now, as a result of absorbing that heat, we've got heat entering our surroundings, that temperature increases. Now, if the temperature of my surroundings is increasing, it's doing so because heat's leaving my system, which means the temperature of my system decreases. Now, if the opposite is occurring, if heat is being transferred into my system, so my surroundings are transferring heat into my system. That means that my system absorbs the heat and the surroundings are releasing the heat. So in terms of my temperature, if my system's absorbing heat, it's going to get hotter. Its temperature is going to rise. And if my surroundings are releasing it, that temperature goes down. So now let's take a look at the question again. We're dissolving lithium chloride. We see a drop in temperature. If we're measuring the surroundings, so if the temperature of my surroundings is dropping, that means heat's leaving my surroundings and it is entering my system. And if it's entering my system, we've got a positive delta H. Now remember, we said ideally we want a negative delta H for something to be always spontaneous. But here we've got a positive delta H. The reason our solution is still going to form is because remember we've got the other component of that free energy, we've got the entropy. We're going to have a large enough entropy gain that it offsets that energy. So this is going to be entropy driven, since it's the entropy that is going to be guiding our solution formation and our spontaneity.